Hi, this video is for Math 2520 and is going to be over section 10.1, 10.2, and it's actually part 2 of that section, those sections. So we're going to look at a sequence and whether it's monotonic. Right, so monotonic meaning it's either increasing or it's decreasing. If it's increasing, then a sub n plus 1 is going to be greater than a sub n, or possibly equal to, but usually it's just going to be greater. And if it's decreasing, then a sub n is going to be greater than a sub n plus 1. So the next number in the sequence is lower. If a sub n is strictly increasing or decreasing, we can of course change those equality signs to just greater than or less than, which a lot of times I've seen it seems like that's the case. Otherwise it just doesn't increase or decrease. Then another definition is bounded above. We'll also get into bounded below. Bounded above is if there exists a number m greater than 0 such that a sub n is less than m, no matter what a sub n is. And bounded below is if there exists a number m greater than 0 such that a sub n is greater than m, no matter how low a sub n goes. A sequence is bounded if it is bounded above and bounded below. So it could be bounded below and still increase and not be bounded. It could be bounded above but still decrease and not be bounded. So it has to be bounded both directions to be bounded in general. Alright, so we want to determine whether the sequence 1 plus 1 over n from 1 to infinity is bounded, and if it's monotonic or not. So here's how we go about doing this. We're going to look at n and it being less than n plus 1. Okay, which is true. 1 is less than 1 plus 1 is 2. 2 is less than 2 plus 1 is 3, and so on. And then we're going to kind of fit it in this form as we go about this. So we're going to divide. Now remember, n is always positive. N is always from 1 to infinity. So we can divide and not have to worry about the inequality sign. So we're going to divide both sides by n plus 1. So you have n over n plus 1 is less than 1. And then we're going to divide by n on both sides. So we get 1 over n plus 1 is less than 1 over n. And then we're going to add 1 to both sides. So 1 over, well, I'll do it the other way. That way it matches up. 1 plus 1 over n plus 1 is less than 1 plus 1 over n. And so now we have what we wanted to have. Okay, so if we add 1 to n, then our number would be less than the original number. Okay, so we do have, because of this, we do have a monotonic sequence. And we can look at this and say, okay, well, if n is 1, we get 2. If n is 2, we get 1.5. And so it's decreasing sequence. Now we have to think about whether it's bounded. Okay, it's decreasing. So it's bounded above by 2. Okay, 2 is going to be the highest number you can have. When n equals 1, you get 2. Now, how low can it go? Well, 1 over n, and when that goes off to infinity, you get 0. So the lowest you can go is 1. So it's bounded below by 1 when n goes to infinity. Okay, so it's a bounded sequence. Okay, all this did was prove that if you have the original, then the next term, original term, next term is less than the original term. That's what that was showing. That's why it's showing that it's monotonic, because you can get something like that out. You know, and it shows that it's decreasing. Alright, so the next one's a sub n equaling n over n plus 1. Alright, so what we're going to do is we're going to look at n plus 1 over n plus 1 plus 1. And when we do that, we get n plus 1 over n plus 2. Okay, well, adding something to the numerator, or adding something to the denominator, and so this is going to be greater than n over n plus 1. Okay, and so we can kind of show this when we can multiply the n plus 1 to the other side, so we have n plus 1 squared, which is going to be greater than n times n plus 2. And we can square this out, so we have n squared plus 2n plus 1 greater than n squared plus 2n. Notice this one shows that it's greater than because there's just 1 being added to it. Okay, so monotonic and increasing. Okay, the next number is going to be always higher than the previous. Okay, so if n is 1, that's the lowest n value, you're going to have 1 over 2. If n goes to infinity, then you'll have infinity over infinity plus 1. Okay, that is basically going to 1. It's getting closer and closer to 1, but it won't ever reach 1. Okay, this is increasing, so it's starting out that your initial sequence starts out at 0.5, so it's bounded below by 0.5 and above by 1. And so it's a bounded sequence. So 2 minus 1 over n. Right, so we're going to look at this and compare 2 minus 1 over n plus 1 and 2 minus 1 over n. Okay, we're adding another term, so on the denominator, so that's going to make that a smaller term. So for example, let's look at it this way. 2, do it in blue. 2 minus 1 over 2 is 1.5. 2 minus 1 over 3 is 1.67. Right, so we look at this as that n increases, this is going to be greater than 2 minus 1 over n. Right, so as n goes to infinity, c sub n goes to 2. And at n equals 1, c sub n equals 1. Right, so it's bounded below by 1, bounded above by 2. But as n increases, this is an increasing function or sequence, and so it's monotonic. Negative 1 to the n power over n. Here, this sequence oscillates between positive and negative values. Right, so absolute value of d sub n is equal to the absolute value of negative 1 to the n power over n, equaling 1 over to the n over n. Here, when n equals 1, you'll get d sub n equaling absolute value of d sub n equaling 1. When n goes to infinity, you get the absolute value of d sub n going to 0. But it's not bounded by the 0 because remember, this is oscillating. Alright, so it's decreasing. And because it's oscillating, it's bounded by negative 1 and 1. Okay. And so it is monotonic because it's decreasing. It's just oscillating back and forth. So absolute value of it should be monotonic. It's monotonic. Right, let's look at the natural log of n. Here the sequence is increasing. Natural log of n plus 1 is greater than natural log of n. And unbounded, since n going to infinity means the natural log of n goes to infinity. So it's monotonic though, because it is increasing. Right, so some other examples, a sequence that's bounded but not monotonic, negative 1 to the n. One that's monotonic but not bounded, negative n squared. It's always decreasing. one that's monotonic but not bounded above would be n squared. One that's monotonic but not bounded at all, you can take either n squared or negative n squared. And one that's monotonic and bounded would be 1 over n. Okay. Monotonic sequence theorem. Every bounded monotonic sequence is convergent. That's why we want to know if it's bounded. If it's bounded and it's monotonic, we know it converges. Okay, so let's determine whether the sequence has a limit and where. A sub 1 equals 1, a sub n plus 1 equals 1/2 a sub n. Alright, so let's start with a sub 2 would be 1/2 of 1, so it would be 1/2. A sub 3 would be 1/2 of 1/2, so it would be 1/4. A sub 4 would be 1/2 of 1/4, so it would be 1/8. A sub 5 would be 1/2 of 1/8, so it would be 1/16. Okay, so we can say that a sub n plus 1 is less than a sub n. So 1/2 of a sub n plus 1 is less than 1/2 a sub n. And then if we wanted to, we can multiply this by 2. So a sub n plus 1 is less than a sub n plus 2. Oh, I'm sorry, less than a sub n. Alright, so this is decreasing. And it's monotonic. If n is equal to 1, then we have a sub 1 equals 1. That's bounded above, since it's decreasing. And if n goes to infinity, then our sequence is going to 0, since these fractions keep getting smaller and smaller. Okay, so this is bounded below by 0. Alright, so we know this sequence converges. So the limit as n goes to infinity, 1/8 of a sub n is equal to 1/2 the limit as n goes to infinity of a sub n. Okay, and if we look at this, L for the limit is going to be equal to 1/2 L. You can set that equal to 0. Factor out the L. And for this to work, then L has to equal 0. So your limit would be 0. And this sequence is going to 0. Okay. In the next video, we'll get into infinite series, which is similar to sequences. I'll see you then.